recording.
सर थोड़ा वेट कर लें, अभी अटेंड आ रहे हैं स्टूडेंट्स.
Earlier in the last lecture we were studying. आज स्टूडेंट्स आ गए सारे, अभी देर है आने में.
सर अभी अभी दूसरी क्लास खत्म हुई है तो स्टूडेंट्स ज्वाइन कर रहे हैं.
अच्छा अच्छा, चलो ठीक है. Assalamu alaikum. I think we have waited more than enough, so we can now start our class. Alright, so in the last lecture, we were studying about analog to digital conversion. So some portion of that chapter was left, which was in the course outline. I will just try to cover that up so that we can move to the next chapter. So we were actually studying in the last lecture, the last portion of the last lecture, we were studying waveform coding. So we were trying to shift our focus on one of industrial schemes for coding of analog to digital streams or digital data. And here we saw that the main emphasis should be on such coding schemes so that you can produce the original signal with high fidelity or with as much possible less distortion. And so these waveform coders, they are robust enough, they can be designed for a variety of sources. So we will be studying some of the basic coding methods. First we studied that was PCM, a very famous coding technique called code modulation. And we saw that there were three fundamental assumptions. First of all, signal is band limited. Sampling is at 2W. If W is the bandwidth, so it will be 2W or higher. The amplitude is restricted, and the quantization levels we said was equal to n, where n is always a power of 2. So that we also said that we can restrict the signal to W bandwidth by using an anti-aliasing filter or using a pre-sampling filter. We can always allow from some guard band, as we discussed in the previous lecture. So this means we can sample at a rate higher than the Nyquist rate, so that we also have a guard band. Now the sample values, they enter a scalar quantizer. So PCM is a scalar quantizer, not a vector quantizer, which is not in our course. Now in scalar quantizer, you could have a uniform as well as a non-uniform quantizer, and selection depends on the actual signal which needs to be coded or the output of the source. That will determine whether we use uniform or non-uniform. Again, the fundamental rule, one of the three fundamental assumptions will be there, that number of quantization levels will be the power of 2. So we know, as we have seen in the previous lecture, that if we have n levels, then we can just have v bits log to the base 2n, which will be equal to v. So v bits will be sufficient. For example, if I have 16 levels. 4 bits will be enough to represent my quantization levels. Or let us say if I have 256, or if I have 32, then 5 bits will be enough, and so on and so forth. You can just find the log 2 of n and you will get the number of bits required to represent all your quantization bits in zeros and ones or in their encoded form, as we have also studied encoding in the last lecture. Now going into a little bit detail of uniform PCM. So first of all, uniform PCM means it is a uniform quantizer. We studied uniform quantizing in the last lecture, which means all the levels are of the same width. Now another assumption is that range of signal is restricted from minus x max to plus x max. And the assumption that number of quantization level is n. So this means for a uniform quantizer or uniform PCM, the size of each quantization region or the length of each region will be total magnitude 2 max divided by n. You can also write it as 2v minus 1, where this 2 comes in the denominator. Now here we have to make sure that the x tilde, first of all x hat, which is your q of x, the quantized value. Here he has written q of x, but in the last video we saw it can be represented by x hat. So x hat is Alhamdulillah, x hat is chosen to be the midpoint of each of these lambdas or each of these tildes. So if they are at the midpoint, the signal value, it could be going only in that tilde region, and if this is the center point, then the total error x tilde, it can be at the maximum going from minus delta over 2 to plus delta over 2. Adi, is this point understood? Samaj, is this point understood? That error can only go from minus delta over 2 to plus delta over 2. As the quantized value is at the center, total width is delta, so the error can go from here to here. All right?
Yes, sir, clear.
Okay. All right. Thank you. Now comes the assumption that first of all, in ordinary PCM, number of levels is usually high. So you can see that the range of variation. So if n is very high, then you can very well see that this delta will be small, because already your x max is fixed. So numerator is fixed and denominator is greater, so delta will be small. And yes, so number of levels is high and range of variation, so x max is small. So these two assumptions are there. N is high and x is small. Smaller, greater, this means your delta will be smaller or small. So if delta is small, then the error within this small lambda or small delta can be approximated by a uniform distribution on this range. So if this is a range, the total width is delta, so uniform distribution will be 1 over delta only within this range. For every other delta region, the PDF will be of a uniform distribution 1 over delta, and the range will be going from minus to plus delta over 2. This is the PCM sampler, then quantizer, which will be giving 7 x hat, and the error will be xn minus x hat. Encoder, it will just for every x hat it will give us some 0 ones. Acha, so here is the calculation. So actually I've done this calculation in my chapter 16 notes. So you can see the detail here. I will also try to explain that. So now we have seen that we try to find signal to quantization noise ratio. The signal power we have seen many times uh, for especially for a zero mean and stationary process, it is autocorrelation at 0, or you can say it is x square fx, or you can say it is a PSD, area under the PSD, and all that we have seen. These formulas we already know how to find the power of the signal. So all of them could be used. Now, but what is the power signal to quantization noise? So what is the power of the quantization noise? I know that noise is x minus q of x, and so the noise power, again you can see that noise, which is x minus q of x, is a uniform random variable and its mean is 0. So if its mean is 0, so its power is its variance. We just find its variance, which will also give us its power. So this will be its power, e of x delta square, and so I'm finding its power. So this is its PDF, which is a uniform distribution. These are the ranges of your uniform variable, and for variance we have x delta square. Becomes x cube over 3. Then you put the limits, lambda cube minus minus lambda cube becomes plus 2 lambda cube, and this lambda cancels with this, lambda cube minus 1, 2 ones are 2 fours are, and this will become lambda square over 12. Now I can put the value of lambda, which was 2 max over n, so 4 x square max over n square. Then I know that n has to be a power of 2 to v. Here p are the required bits. This becomes 2 square. You can also write 4v. So this will be your power of the quantization noise. So the signal to quantization noise ratio, and px you can find the various ways, will be px divided by this thing divided by this thing. So its numerator will remain here, but its denominator will come here. If I take its 10 log of this will be one thing, plus 10 log of 3, and 10 log of 4v. So this becomes 0.4, this becomes 4.8, and this becomes 6v. So this means if I increase my levels to next higher power of 2, this means I'm increasing my 1 bit. Let us say bits were 3 bits, 8 different levels. Then I increase it to 4 bits, so I have 16 levels. So by increasing 1 bit, I am increasing my dB. XS signal to quantization noise ratio in dBs is increasing by 6 dB. So same thing is discussed in the book, so that you can see here also. But here one thing is also there, that the signal power, which is ex square, and we know that this ex square will be actually always less than x square max, because x square max is its maximum value. So expected value of x, where x is going from 0 to x max, will always be less than x square max value. And in the SQNR we just saw that you are getting px over x square, both here and both here. So px over x square, as px is less than x square max, so px over x square max will always be less than 1. So XQNR will always be upper bounded by 3 into 4v, that will be its maximum value. And this also shows us that in uniform PCM, if your signal power decreases, if your px is decreasing like this, then you can very well see that your SQNR, that will also be decreasing. All right. Yes. So as the dynamic range of the source increases, the SQNR will be actually decreasing. So increasing of the dynamic range of the source means that the source is taking more values from 0 to some higher value of x max, some greater value of x. This means its dynamic range has increased. So increasing the dynamic range of source will result in decrease of px over x square max, because x square max will be increasing because your dynamic range is increasing. So your this value of px over x square max, this will be decreasing. So if this is decreasing, px over x square max is decreasing. This and rest of them are constant. So this means that SQ and R will also be decreasing. So the same I told you, especially in decibel, and this I also discussed. So if you want to increase or decrease, or you want to estimate how many bits are required to achieve a SQNR, you can just see this equation and it will give you the relevant value of V to get the desired SQNR. Now the SQNR, an example for a uniformly distributed signal, when uniform PCM is applied with 256 levels. So first we find the signal's power, which signal is uniformly distributed now. In this range it will be 1 over 2 x square dx, which we have actually already found in chapter 5, and you can again check. This comes out to be 1 over 3. So your x max will be equal to 1, v will be equal to log of 2, which is equal to 8. Just put the values in the SQNR formula. This here x max is 1, so no need to write here. Just multiply and you will see that your SQNR in dBs comes out to be 48. So bandwidth required for PCM. So we saw that if the bandwidth is W of the actual analog signal, then sampling frequency has to be 2W samples per second. If you add some guard band, then your sampling frequency will be greater than 2W. Let us say it is Fs is equal to greater than some 2W, or it is equal to 2W. Let us say it is Fs. So, but we know that for Fs means you are getting Fs samples per second. But for each sample, now you have V bit of representation. So you will have V into Fs bits per second. If Fs is equal to 2W, this will become 2VW. The minimum required bandwidth for transmission of R bits per second is R over 2. Alright. So the details, they will come in the appropriate chapter. Here you just have to see that if I want to transmit 2VW, then I must have a bandwidth of VW. Or in other words, if I want to transmit VFS bits per second, I must have a bandwidth of VFS over 2. Or in terms of Nyquist rate, Fs is 2W, this becomes V into W. So this means that the PCM expands the bandwidth of the original signal by a factor of V. Then we have non-uniform. Why we use non-uniform? Because the signal coming from the source is not uniformly distributed. Input signal is far from uniform. For example, in a speech signal, higher probability for smaller amplitudes and there is lower probability for higher amplitudes. Therefore, it makes sense to have a quantizer that have more quantization regions at lower amplitudes and fewer quantization regions at larger, which means delta size will be smaller for smaller amplitudes, while this same delta size of the region will be variable. It will be small for smaller amplitudes, while for higher amplitudes it will be large. So this delta will be non-uniform. So quantization will be of various sizes. Now, how can we perform uniform quantization at industrial level? So first thing is that samples are passed to a non-linear element that compresses the large amplitude, reduces the dynamic range of the signal, and then perform a uniform quantization on the output. So first of all, you will compress the large amplitude, so reduce the dynamic range, and then you will just put it to the same uniform quantization because the amplitudes have been reduced and now we can have uniform quantization. All right, so we will compress and then we can inform uniform quantization. At the receiving end, what we will do, we will apply the inverse operation of this compression. This will be called expanding to uh, get back the original signal. So a diagram is shown here. So you have a compressor. When you apply uniform PCM, so it is sent to a channel. Then finally your decoder, and then we have a expander. So decoder will give us uh, the signal, but that signal will be compressed. So we will expand it, and uh, then we can apply to reconstruction filter to get back the original signal. So everything is similar to a uniform quantizer, but we just introduce a compressor and an expander. So various types of this compressor expander, that will be called a compander or a companding technique. So in industry, companding is performed by a mu law compander. There are two types of compander. One is a mu law compander used in USA, Canada, also in Japan, and it employs this logarithmic function for compressing. So you can see that log has the property smaller values are enhanced and higher values uh, are reduced by the help of log. That log operation will be used here, and different signs of mu will give you different types of compression. Uh, so in the US and Canada, this mu is 255, and then you have a uniform quantizer after this, which has 8 bits per sample, and this gives us a 24 dB of gain. Its characteristics is shown below. You can see for U0, actually straight line, you have no companding or no compressing, but as mu increases, you can very well see that you are boosting the smaller values, but the higher values, you can very well see they are being compressed. Other compressor or compander is this logarithmic, also called A law compander, and its characteristics are there. So its performance is also comparable, and you can see here again, this is a straight line, and as A increases, you will get more and more compression of higher values. So this completes our chapter 7. Here, some points I will also try to discuss with respect to the notes of Dr. Muhammad Tahir. So because there was some additional information there. Otherwise, even if you go to the book, you will be course is still covered, but just for explanation, some very good graphical descriptions are there. So you can see here, this was your sample signal, and but so sample signal will lie between, this is just the PCM, we have just discussed PCM, and it is a pictorial description of pulse coding. So these are your continuous values, amplitudes could be continuous, time is discrete here. Now for every other value, it will be lying within this quantization region, but for this quantization region, I will take only one value. So let us say this is the value, so I will be taking x delta, so this will be the amount of error which we have denoted by x minus x hat, sorry, x hat is a quantizer, which will be equal to x tilde. Again, we saw this we have already seen, and you can see here that actually input signal was stochastic and this was deterministic. This was also stochastic, but once we sample the stochastic values at some discrete time, they will all become a random variable. So that is why this was a random variable input, and this was also. So in PCM, we directly assume under the considerations that we can take x tilde to be a uh, uniform random variable. This I discussed, all of that has been discussed, so no need to revise. And you can find its power, which will be equal to variance because mean is 0. This I have also discussed. Mean is 0, you can see here. So variance is equal to the p of x square, which is equal to the power. And again, this was uniform where all the intervals are equal. Yes, for uniformly distributed signals, uniform quantization is optimal because signal could be anywhere. But if it is not uniform, then uniform quantization will become suboptimal. For example, we just saw it for the speed signals. Speed signals. So this is for a speed signal. The more of the probability of this lower amplitude signals have more probability as compared to higher. That is why we will have non-uniform quantization. So more quantization for lower amplitudes we discussed also. So this will help us to achieve the same SQNR at different amplitudes of the message signal. Because for lower we have high amplitudes at different amplitudes of the message, the same SQNR. Even for lower amplitudes, we will actually expand them so that you get the same error for any type of magnitude. This was a U-law compounder, this was a A-law compounder. Both are used for compression and expansion. So non-uniform is that you apply uniform, but before uniform you apply this compression compounder, the compression and then expansion at the end, so you will get back your original signal. So you can see this is non-uniform. Lower values you have lower intervals, for higher values you have greater intervals. And you can see that for uniform quantization, if power is decreasing, power in the signal, which we actually can map it to an SQNR. So if just the power is decreasing, this means that SQNR is decreasing. So for non-uniform, if power is decreasing, so noise power will also decrease, hence XQR will almost remain constant because numerator and denominator are decreasing at the same time. And इसको इस टर्म्स में लिखा है सर ने, वो भी ठीक है, बट नॉर्मली इन इंडस्ट्री वी यूज दिस इन टर्म्स ऑफ द डायनेमिक रेंज, जो भी मैंने आपको पहले बताया था बुक से, ज़्यादातर डायनेमिक रेंज के साथ होता है कि what will happen to the SQNR if the dynamic range of the uniform or the non-uniform quantizer is increased or decreased. सारा कुछ, this I've already shown you 6V and all that. Encoding was already done, so we have also covered cell lectures. This means we have completed our chapter 7. Now we will move to chapter 8. If you have any questions, you can ask. Alright, chapter 8 is a very important chapter. It's a long chapter. It will take also multiple weeks, and and you could see in the past papers more than 20 marks questions are set from this chapter. So this is also very important, especially nowadays when we have digital communication, and as well as signals are actually analog once they are sent in the channel, but we have digital processing, and the basic channel is again the famous additive wide Gaussian channel, which we have studied in chapter 1 also. Signal plus noise, that is the receive signal. So how you will do this modulation, how can you combat noise, what will be the error, probability of error, and all that will be covered in this chapter. So we have seen AWGN is one of the fundamentals, also a model for many channels. Now here we will focus on design of waveforms that can carry my digital data through this AWGN channel. So we are assuming that we have discretized our data. Our data was analog, but we have made it digital. Now that digital is to be sent through a channel. So that channel could be simple baseband, which we have studied in chapter 6 also. Baseband means there is no carrier modulation. The frequencies, let us say at low pass frequencies or baseband frequencies or message signal, the channel is also at the frequency of the message signal. You didn't have to translate, you didn't have to modulate your signals to some higher frequency. So no use of carrier. But we also know that in many communication channels you need a carrier, and you have to modulate your signals on a carrier so that your signal is sent after modulation inside the appropriate band of that company or of that institution. The signal is transmitted by carrier modulation. Baseband and carrier modulation are both there. You can say baseband and band pass. This we have discussed in the previous lecture. So we will begin this chapter by a geometric representation of these signals. So question comes, why do we need to have a geometric representation? The main reason is that it simplifies our calculation. If you won't go into the geometric representation, you will be engulfed by the mathematics or you will be in deep trouble. So remember to always represent your signals geometrically. We will be seeing it in detail now. Uh, uh, Once we have done its representation geometrically, we will also see its demodulation and detection, and we will also calculate the performance of various schemes in this AWGN channel in terms of probability of error. So geometric representation. So I've told you already for simplification. So first of all, I will try to explain this with the book, but after this, in the example, some of the steps are missing. So I'll refer to the notes of Dr. Tahir. So those missing steps will be given in the notes, as is our usual scheme of things. So geometric representation of signal waveforms. All right. Let us ask one question before we go further. Saman Jamil sir, can you hear me?
Yes, sir.
Acha. Uh, have you studied orthogonal signals in linear algebra?
सर
Or your
ऑर्थोगोनल
what is
वेक्टर्स
your
पढ़े थे.
अच्छा orthogonal
ऑर्थोगोनल
vectors
वेक्टर्स
पढ़े?
पढ़े थे.
वो तो सिर्फ वेक्टर फॉर्म में डायरेक्शन के हिसाब, जैसे हम ईएमटी में पढ़ते हैं ना, एक्स और वाई कोऑर्डिनेट आपस में ऑर्थोगोनल हैं.
सर वो पढ़ा था कि वेक्टर्स का अगर डॉट प्रोडक्ट 0 हो तो वो ऑर्थोगोनल होगा.
अच्छा अच्छा, यानी ये आपने लीनियर अलजेब्रा में पढ़ा था?
जी सर, एलए में पढ़ा था.
अच्छा अच्छा, ठीक है, सही, ठीक है, ऑलराइट. सो बट ऑलराइट, गुड फीडबैक. सो यू कैन सी दैट there you have studied just in terms of vectors, but here we are trying to design our communication systems. We need a mapping to represent our actual analog signals in terms of these vectors. Then we can say that these vectors are orthogonal, or they are independent, or the dot product is 0 and all that. So we don't have to just study the mathematics, which you might have studied in your previous courses. Here we have to link it with the real world, with the physical signals. So we have seen in digital communication what is happening. Your data is now encoded with all that quantization, sampling and all that. Now it is just zeros and ones. All right. Now what we need to send these zeros and ones in an analog channel. All right. So, but in the analog, you cannot send 0 1. You need some representation. Analog world is the real world. So you need some analog waveforms to send your digital bits, which have come after all that sampling, quantization and encoding. So let us say one way will be that I take one bit at a time. My bit could be 0 and 1. Whatever encoding technique, whatever quantization, it is 0 and 1. All right. So I say, all right, I send S1, let us say for 0 bit, and S2 for 1 bit. S1 is an analog signal that will represent the 0 bit, in my channel, just for an assumption, and S2 is the signal, analog signal, that will represent my 1 bit, मतलब जो bit की value whenever you get the bit value 1 in my analog channel. So this type of digital modulation, where you now represent your digital data in terms of analog signal, is called binary modulation, because you are using two types of distinct signal waveforms to represent your zeros and one. Achha. But at the same time, what could happen? You say, no, I do not want to send 1 bit at a time. Let us say I want to send 4 bits or k bits at a time. So if I am using 4 bits, this means I would need 2 to the power 4 signal waveforms. This means I will need 16 waveforms. So if I send any of those 16 waveforms, they will represent a distinct 4-bit. Because if you are taking 4-bit combination, so you could have 16 different combinations. So for all those different combinations, you would need 16 different analog signals. So if you want to send k bits, you require 2 to the power k distinct signals. Represent them in the analog channel. And this type of digital modulation, the first one was binary, and this will be called Mary. So in this course, for the first time, we will also be covering Mary modulation scheme. Previously, you could see that we were not covering this Mary modulation, and still, a large part of the finals was covered by this chapter. Now we are adding another part, Mary modulation, so this chapter becomes more important as ever. Now in this first section is the geometric representation. We will try to develop a geometric, or in other words, you will see a vector representation for our signal waveforms. And this is a very, very important representation. First of all, I've told you it simplifies the analysis. Another thing, that the simplification is so unique that by just looking at this vector representation of signals, a good communication engineer is able to gauge its performance in an AWGN channel, and from that idea, you can choose the best scheme for higher generation communications in complex time varying or LTI channels, for multiple users of 3G and 4G and now up to 5G. So this is a very, very important section and chapter. Fundamentals of communication will be covered here, especially of digital in noise. So let us try to first of all understand this geometric representation, this compact representation, this compact characterization of our representation, vector representation of our digital signal waveforms. So let us say that we have M signal waveform. You are given, let us say, 20 waveforms, that you are given that those could be sent over a communication channel for which you have to design. So these waves, when we say they will be very good, they can be sent through a communication channel. You will say, all right, but we have to represent them geometrically, and we will just represent a part of these M waveforms, and we will see that that number will come out to be n. We will not be using all those M waveforms, rather we will be using n which will be less than or equal to m. So because you will see that some waveform may be linear independent, might be linearly dependent on the other waveform. So that dependent waveform will not be used, because that will not give us an orthogonal set. So from this M signal waveform, we try to find n signals which are less than or equal to m, but those n signals must be orthogonal to one another, that we will be seeing here, or uh, alright. So how to choose those n from m? We have the famous principle which is called the Gram-Schmidt orthogonalization procedure. So that we'll be using. So very important. It gives us an idea of how to get these vectors, which you can use in your linear algebra, but how to transform the analog to those vector form, this will be covered here. So let us say we have one signal S of 1, we find its energy. Haji, does everyone know how to find the energy of the signal? Haji Hasib Zahid Saab, do you know how to find the energy of a signal? X of t is the signal. How can I find its energy? Can you hear me, Hasib Zahid Saab? Roll number 170. ये तो खामोशी हो गई. All right, Saman Jameel Saab, can you hear me?
Yes, sir.
अच्छा, ये मैंने पूछा था कि अच्छा ये शायद आपको पता ही हो आप तो. So do you know how to find the energy of a signal x of t?
सर वो उसके मोड ऑफ स्केट का मैग्नीट्यूड के
हाँ,
स्केयर उसको
very good.
इंटीग्रेट कर लेते हैं माइनस इनटू.
Yes, yes, yes. I have told you many times. I know you have also studied this in your previous courses, but again we also repeated this in chapter 2. That first of all, xt is the instantaneous value. Take its square. Once you take its square, this becomes instantaneous power. Then you integrate x square t over full-fledged its time integral infinity dt of x square t. So that will give average power integrated over time, that will give you energy. Alright, that's another thing, that if you want to find the power of this signal with energy signal, it will become 0. But with the power signal, you divide it by t limit t infinity, also limit infinity t over 2 t over 2 लिख लीजिए भी, t tends to infinity, you will get the average power. Okay, but here remember that all those signals, analog signals that you will use to represent our binary modulation signals or our Merry modulation signals, मतलब वो देखें वही जो होगा ना, 2 अब 1 बिट को रिप्रेजेंट करेंगे, 2 बिट को रिप्रेजेंट करेंगे, तो फिर आपके पास 4 सिग्नल्स होंगे. So all these signals, they are energy signals. They are limited in time, so that you have their finite energy. And once they are limited, then you can very well find the energies. Find the instantaneous power, x square, integrate, and you will get the energies. हाँ जी हसीब जाहिद साहब, आप खामोश कैसे हो गए? आपने बड़ा 2 मिनट हमारा लेक्चर भी लेट किया था. Alright, coming back to the lecture. So you have S1, you will just divide S1 by the under root of the energy. Alright, so E1 is the energy. Alright, So once you under root, this means they're gonna even gives you the energy squared energy. It is energy, but you know you have to square and then energy comes from the power. So once I take its under root, I'm in a way finding its you know the normalized, or I'm finding its maximum amplitude in a way, you can just say. And once I'm dividing this by under root, this means I'm normalizing my signal. So by the help, when you will see, once you normalize this by delta E1, the same S1 can be written as this psi1, where psi1 will have unit energy. You will say, why is a unit energy? Because you know, if I find its energy will be equal to energy of this. Energy of this will be energy of S1 divided by square of this one. So this square, this becomes, you know, E1, and you know, energy of this is actually S1 square integral, which is again equal to E1. E1 divided by E1, this becomes 1. So energy is normalized if you divide the original signal by the under root of its energy. Remembering the fact that the signals here are energy signals. हाँ जी, समझ आ गया आप लोगों को? अरे सलमान साहब, समझ आ रहा है इसकी एनर्जी यूनिट क्यों हो जाएगी?
सर अभी पूरा क्लियर नहीं है, वैसे देख रहा हूँ, समझ आया, लेकिन
नहीं, आपको पूरा भी दिखा देंगे इंशाल्लाह. वैसे आप रफली देखें ना भाई, इसकी एनर्जी 7 की इसके बराबर है.
सर
वो इसकी
वो आइडिया हो गया, लेकिन ये मुझे ये नहीं समझ आ रहा कि ये स्क्वायर रूट E1 से डिवाइड करेंगे तो ये यूनिट नॉर्मलाइज 1 क्यों हो रही है, मतलब नॉर्मलाइजेशन क्यों है स्क्वायर रूट ऑफ एनर्जी से डिवाइड करने से?
हाँ, वही तो कह, नॉर्मलाइजेशन इसलिए हम कहते हैं because the energy of this psi1 becomes 1. That is why we say we normalize it by dividing it by delta E1. देखिए सिंपल है ना, आपने ऊपर इंटीग्रेट किया, वो एनर्जी तो आएगी E1 ही आएगी. इसका स्क्वायर भी ले चुके होंगे आप एनर्जी के लिए, तो ये E1 डिवाइड होगा, एनर्जी आपकी 1 हो जाएगी. इसे कहते हैं नॉर्मलाइजेशन. तो जो आपने नए सेट्स बनाने, नए जो सिग्नल्स बनाने हैं, उसमें हर एक की एनर्जी को 1 होना चाहिए, यूनिट 1 करने. तो उसके लिए क्या होगा कि जो वट एवर द सिग्नल दैट यू हैव चूजन हैज टू बी डिवाइडेड बाय इट्स एनर्जी, अंडर रूट ऑफ एनर्जी. Let us go further. Alright, this was your psi1. Now I want to construct psi2. But first of all, you have to make sure that in constructing psi2, there should be no portion of in psi2 of S1 or of psi1. All right. So what I do? Okay. First of all, you find the part in S2 of psi1, the dependency or the dependence, the linear dependence portion in S2 of psi1, that is called C21. Just find this value C21. It will be just S2 times psi1 integrated over. एक तो से आप डॉट प्रोडक्ट ही ले रहे हैं इसका, मगर डॉट प्रोडक्ट असल में एनालॉग में लेना होगा ना. फिर ये वेक्टर फॉर्म आएंगे, वेक्टर फॉर्म में जो सारा जब आप लगा रहे हैं, जैसे आप पहले से पढ़ते आए. So you just multiply your S2t, the second signal, because now you want to find psi2. Psi1 has been found by just dividing it by S1. For psi2, you have to make sure there's no portion of S1 there. So first of all, what you do, you take the dot product, or you take the projection of the second signal onto the first orthonormal vector. This gives you C21, projection of 2 onto 1. Now this C21 times psi1, चूंकि आपने प्रोजेक्शन निकाला है on S2 of psi1, so you just multiply this C21 by psi1. This will give you the part of the signal of S1 present in S2 that needs to be subtracted. So you will just subtract from S2 this projection of psi1 onto S2. So D to T will come out to be an independent signal from psi1, or in other words from S1. But we know it is not normalized, so you just divide this by its energy eta 2, whatever D2 you have found by subtracting the projection, you just divide that by its energy. Hence now you will get the normalized second signal, that will be psi 2. Again you can see energy is always equal to square of the signal. Here remember, this psi 2 will be the energy of D2, that you are able to normalize psi 2, or energy of psi 2 will be 1. Alright. So for any, this for psi 2, psi 3, psi 4, you can do it like that. For every psi k, it will be equal to its relevant dk over its energy of dk, and every dk is found by its relevant sk minus all the projections of all the previous orthonormal signals onto this skt. That is all subtracted, hence you get dit. So hence you will get this thing, and you will be getting the psi k, which will be normalized, as well as they won't have any projection of the previous orthonormal vectors. So this process will continue until all the m signals have been exhausted. So you might get normalized vectors equal to m or less than m, because you will find that there will be some vectors, some signals, which will be totally dependent on the previous orthonormal vectors. Alright, so they will totally dependent by this, hence the dk will be 0, hence they will have no error or no quantization error. So our set will be n, which could be less or equal to m. So these n orthonormal waveforms, which are orthogonal to one another, they form the orthonormal basis in the n-dimensional signal space. Dimensionality will be n. It can be equal to m if all the signals are linearly independent. And if we found that all the signal waveforms, they are so this comes out to be orthonormal basis, and this you will just see in how to represent this vectorially by vectors. And if all the m are independent, then n will be equal to m, and none of the signal waveforms could be ignored, because every signal waveform is not given as a linear combination of every other signal waveforms. So your n will be equal to m. Let us see at this example. Again, an important example. So problems always come in representing signals geometrically. Let us try to understand this from the book. We will also refer to the notes if you have some confusion. And even if some steps are missing, I will go to my notes. So मेरे ख्याल से notes पे चले जाएं. Again many steps are missing, you can just see from here, so we can go to the notes here. Are the notes visible? आई नोट्स नजर आ रहे हैं आपको?
जी सर.
अगेन लेट अस जस्ट ये देखने सर ने शुरू में भी कोई अच्छी बातें बताई हैं, अगर देखना तो ये देखने मैंने आपको यही बताया था. मैसेज सिग्नल है, सारा कुछ करने के बाद इट इज नाउ 0 1s. नाउ वी आर डिस्कसिंग दिस पार्ट, हाउ टू रिप्रेजेंट our digital signal with respect to signals. The signals could be married, they could be binary, and then we will represent these signals geometrically that we are trying to understand. So this was a model for the low pass. Just you have noise added to this baseband signal, or low pass communication, baseband communication, baseband channel. But many times we have a pass band channel. और बैंड पास भी कह सकते हैं. So in baseband you have no carrier, but there you have carrier. इसमें आप देख लेंगे signal waveforms, they are modulated onto a carrier जो हमने एनालॉग एफएम में पढ़ा था, and then they will be transmitted. So we have these M signals, and we want to find the orthonormal vectors which will be used for their representation. The condition will be that each orthonormal vector will be normal to one another. You can see it is 0 or independent, and the energy of each orthonormal waveform or orthonormal signal is equal to 1. So the principle that I have already discussed, S1 energy divided by S1, then projection of S2 onto psi1, then subtracting this from S2, subtracted signal normalize, and so on and so forth. This will continue. This we have discussed when we know. Now let us look at this example. Same example in the book, no change, but you know the steps are there. Just look at those steps. So first of all, we have S1. You could see here. So what is the energy of S1? All right, so we 1 square, 1 square, 1 time, and you can see that the energy comes out to be 1 plus 1 2 under root. You can just take it square, which will be 1, and integrate, you know, the area in the curve is 2, so this energy will be 2. So I will just divide S1t by its under root of energy, which is under root 2. Right, so height will now be, S1 will now become psi 1, height will be equal to 1 over under root 2. You can see here also. So psi1 will be just the same signal as 1, only its amplitude will be normalized by under root 2. Now we have S2. Now S2 is this thing. So first of all, as ever, this we have done. Find the projection of S2 onto psi1. And very simple, the steps are already given here. Psi1 was 1 over under root 2, 1 over under root 2 in both the intervals from 0 to 2. And S2t is 1 in interval from 0 to 1, while it is minus 1 from 1 to 2. This comes out to be 1 over under root 2, area of the curve is 1. This comes to minus 1 over 2. So this means C21 is 0. And there is no dependency of S2 on psi1. So just from this you can also see in the figure here, if you take the dot product of these two signals, you can see 1 1, this becomes minus 1, so 1 minus 1, this becomes 0. There will be no dependency of S2 on psi1 or S1. This comes out to be 0. So your D2 will be, because D2 and 0 will be just equal to S21. S2, energy of S2 again you can see 1 1, which becomes under root 2. So this will be your psi2. Psi2 is just S2 divided by under root 2. You see here it is just S2 divided by under root 2, and this will be your alright. So psi2 has also been determined just S2 divided by under root 2. Now let us see what is psi3. Again it will come from S3. First I will find the projection of 3 on 1, then I will find the projection of 3 on 2. So remember, this will be 3 on the first normalize, and this will be 3 on psi2, this will be 3 on psi1. So just for a rough comparison, you can very well see here 3, you can know this is actually also psi1, just we have to normalize by under root 2. So S3 on S1, you can see this will be negative, second portion will be positive, and this will be 0 because there is no 2 to 3 here. This product will be 0. So their two products will give you minus 1 plus 1, this will be 0. Similarly, S3 with S2 normalized, you know this becomes psi2. Again you can see plus 1, this will be minus plus minus, minus plus will be minus. So yes, this will be minus here, this will be minus here, and this will be portion will be 0 product. So you know minus minus, yes, this will be giving you certain value, and projection of psi2 and S3 will not be 0. तो आप देख लीजिए 1 over under root 2 होगा तो ये minus 1 over under root 2 हो गया, और ये भी minus 1 over under root 2 हो गया. तो minus 1 over under root 2 into minus into plus minus, this becomes minus 2 over under root 2. So this becomes minus under root 2. This becomes minus under root 2. All right. So once we have find the projections, now you can find D3 will be S3 minus C31 into psi1. But C31 is 0, this goes away. Minus C32 into psi2. So C32 is this, psi2 is psi2. So this gives you your D3, which is actually orthogonal to both psi1 as well. It is orthogonal to psi2 because whatever part that was dependent has been taken out. Now you need to find the energy because you have to normalize this. So you need to find its energy. So there are various ways. One thing that mostly I used to do, I used to draw first of all D3 और फिर उसकी energy निकालनी है. But it is not necessary. You don't have to draw. You can also do directly. अब आप खुद ही देखें ना कि इसमें once I will subtract, so this means this total portion has been zeroed because these two portions were the dependencies, and I've actually subtracted this portion from this portion, so this actually has gone away. You can also check, only this portion is left 2 to 3, and you can see that its energy is just 1. All right, but other way mostly used as given by Dr. Tahir is that you use this equation and find its energy. No problem, you can do that. So D3 square will means square of this whole. This will be a square plus b square minus 2ab. So a square will be s3 square, under root of s3 square will be the energy of s3. Energy of s3 will be what? It will be same thing. 1 plus 1 plus 1, it will be 3. Alright. So energy of s3 will be 3. And what is the energy of this? Alright, energy of this means square of this becomes 2, this comes out, integral of psi 2, integral of psi 2 is 1 because energy of psi 2 is 1. Psi 2 का square भी लेने कुछ फर्क क्या पड़ा, psi 2 square under root integral of dt is 1, so this is totally 1. You just get 2 here, so its energy is 2. Then you have minus 2ab, alright, so minus 2 times s3 times psi 2, and you have that also minus 2 this, so minus 2 goes with minus 2, this becomes plus 2 under root 2, and s3 into psi 2 has already been found, alright, and s3 into psi 2 we saw this, it is c32, which comes out to be minus under root 2, alright, so 2 times minus under 2 into minus under root 2, this will give you 2 to the 4, so it will give you minus 4, alright, so this gives you 1. Both this is correct as well as the other way is also correct. So once you find the energy, which is 1, so d3 divided by 1 is your psi 3, so you have found psi 3. Alright, the time is up. We will continue from the this point in the next lecture. Haji, if you have any questions you can ask. Alright, no questions, so I will end the recording.